Hello, all you biochemists out there, and welcome to my, guess what, online lecture that I should have lectured on last Thursday. I apologize for not being in lecture on Thursday, but I hope that this online lecture will help to kind of cover what we should have covered then. So if you thought you could kind of get away with biochemistry on Thursday and just kind of celebrate, we're going to celebrate some more right now. So let's go ahead and continue on where we left off from Tuesday, and hopefully you'll have all of these lectures down by the time you come back in for lecture. All right, let's go ahead and start. We're going to continue on with our discussion of buffers. A buffer solution here maintains the pH by neutralizing small amounts of added acid or base. An acid must be present in order to react with any hydroxide ion that is added, and a base must be present in order to react with any hydronium ion that is also added to there. Now, one of the main things that buffers do is that they help to maintain a designated pH until it can no longer do so. So buffers will help maintain that, but again, buffers have a limitation to how much they can do so until finally they're overpowered and the pH and the hydrogen ion concentration solution is going to change. Right. So when an acid or a base is added to water, the pH will drastically change because water is not a buffer. Whoa. Is not a buffer. Okay, water here is not a buffer. So when an acid or base is not in a buffer solution, the pH is maintained. The pH does not change when an acid or a base is added because the buffer molecule itself will either take up hydrogen ions or give back hydrogen ions into solution in order to maintain that pH level. Now don't forget that pH is a measure of hydrogen ion concentration in solution. As you can see here, we have a solution that is at a pH of 7 in water. If we were to add hydronium ions or protons into the solution, the pH is going to drastically here drop to 4, for example, because there's nothing to take away those hydrogen ion concentration that's dissolved in solution in order to maintain that pH of 7. And the same can go for here of a hydroxide ion. When a hydroxide ion there is added into solution, it's going to go ahead and steal away, or not actually steal, but bind away hydrogen ions that were already floating in solution back onto that buffer molecule, and then therefore raise that pH up a little bit higher. In this example, we see here at a 10.5. Now the pH 7 here, if it were in a buffer solution, if we were to add hydronium ions or protons into the buffer solution containing buffer molecules, the buffer molecule is going to go ahead and it's going to take up all of those hydrogen ions that you just added into that buffer, at least to however much it can. And then by doing so, the pH compared to that of water did not drastically change. You've got here around a 6.9. But in a buffer solution, if we were to add a hydroxide ion, same thing here. The hydroxide ion is going to therefore steal away hydrogen ion concentrations from solution. However, the buffer is going to say, oh no, that's not the way it's supposed to be. So the buffer molecule, which may have some hydrogen ions attached to it, is going to release out those hydrogen ions into solution in order to bring it back to where it's supposed to be, at least to the best that it can. And as you can see in this case, the pH here is stuck. At least it doesn't climb too much like it did before, and it only went up to around 7.1. So the buffers help to maintain the best it can that solution. It might fluctuate by what, 0.1 or 0.01, but that's not a drastic difference. So once again, just kind of review what I talked. Buffers work because they resist changes in pH from the addition of an acid or a base, and in the body they absorb a hydronium ion right over there or a hydroxide ion from the food and cellular processes in order to maintain that pH. Once again, pH is the hydrogen ion concentration in solution. They're important in maintaining functioning of cells and blood, and they maintain a pH of close to 7.4 in blood. Now, what's quite amazing in a microbiology situation, if you're trying to test to determine, if you're trying to test to determine how a particular microbe reacts in the body, a lot of times there's nutrient agar or some sort of agar gel that is used in order to help grow these microbes. And a lot of times these microbiologists will try to maintain the pH of the agar at 7.4 in order to mimic the environment of blood, or mimic that. So anyway, just some cool tidbit for you. Now, a change in the pH of the blood affects the uptake of oxygen and many cellular processes as well, because hemoglobin is a protein and it is affected by the hydrogen ion concentration in solution. Now, a buffer solution contains a combination of acid-base conjugate pairs, a weak acid, and a salt of its conjugate base, such as we have here its weak acid dissolved here in aqueous solution, and then we also have its conjugate base, which has already released out that hydrogen ion right over there. Don't forget that our definition, at least that we've been talking about in lecture, is that an acid, one of the definitions, that it releases hydrogen ions into solution. In this case, we do have a weak acid. It does release out that hydrogen ion into the solution, therefore leaving it with its conjugate base and a charge. Has equal concentrations of a weak acid and its salts as well. Now, in the buffer of acetic acids, you can see that was HC2H3O2, the sodium acetate, sodium here, and we still have those molecules, that sodium ion right over there. The salt produces acetate ions and sodium ions, and once again, as you remember in lecture, that sodium ion, when manufactured by a lot of chemical companies out there, they add that sodium ion in order to kind of help resist this molecule from easily reacting with other molecules out in the environment. So that sodium ion acts as a shield away from that negative charge in order for us to kind of manipulate it and then use it later. We can drop that sodium ion later in a reaction that's more favorable. Now the salt, okay, so we have here sodium acetate, we write, and it's dissolved here in aqueous solution, and when mixed in with water, oh my gosh, my pen's not working the way it's supposed to. When it is dissolved in water, that water gets in between the ionic interaction between the acetate and the sodium ion, and it slices them away, and that sodium ion drops out, and then therefore releasing that acetate ion into the solution. So you can see here the large amounts of the large amounts of acetic acid right over here mixed in with H2O will produce large amounts of acetate ion, and we have here that hydronium ion as well. Okay, once again, if you didn't catch it, don't forget that there's tons of water molecules in solution, and that oxygen on the water molecule is going to go and grab on to that hydrogen ion, the hydrogen atom on the acetic acid, and therefore pull it away from that. Now, the function of a weak acid in a buffer is to neutralize that base. Now, the acetate ion here produced in the neutralization reaction adds to the concentration of acetate already in solution from the salts. As you can see, we have an equal concentration of acetic acid and the base. And when we add the hydroxide ion into solution, the hydroxide ion is going to go and steal away that hydrogen atom from that acetic acid, because again, it's an acid, likes to dump out hydrogen ions into solution, and therefore that bond right over here of electrons is going to come back over here onto acetic acid, and therefore producing that acetate ion. Same thing here, the function of an acid ion is to neutralize acidic hydrogen ions from acids. So the acetic acid here contributes to the available weak acid. We have here an acetate ion in acetate ions right over here, and we also have the acid, more weak acid compared to that of its conjugate base. And so in the addition of as you can see here, the hydrogen atom, the acetate ion, is going to steal away that acidic hydrogen ion from that hydronium ion right over there, and then form the acetic acid, and then of course water, therefore contributing to equal concentrations of those two. Buffers work because the weak acid in the buffer neutralizes base, and the conjugate base in the buffer also neutralizes the acid. So as you can see, the buffer described here consists of about equal concentrations of acetic acid and its conjugate base, acetate ion, adding a hydrogen ion into solution, or in this case a hydronium ion, to the buffer reacts with the acetate ion, whereas adding the hydroxide ion is going to neutralize acetic acid. So the pH of the solution is maintained as long as the added amounts of acid or base are small compared to the concentrations of the buffer components, meaning that as long as the buffer has available hydrogen ions or atoms to contribute to the solution, it can definitely make the solution a little bit more acidic if the molecule like a hydroxide ion is taking away those hydrogen atoms from solution, or if there are available slots in the buffer molecule to accept those hydrogen ions in order to bring the solution pH right back up. So again, that buffer is going to work in order to kind of donate or accept hydrogen ions in order to maintain that pH. Okay, which of the following combinations make a buffer solution? You guys can do this on your own. The solutions are provided for you in your PowerPoint slides. All right, moving on. Reactions of acids and bases. Now, gastric acid contains hydrochloric acid, HCl, and is produced by parietal cells that line the stomach. What's really amazing is that the lining of your stomach isn't invincible against this hydrochloric acid. The hydrochloric acid produced will also kind of dissolve and disintegrate the membranes of the gastric lining, endothelial lining, and so therefore your cells, you got a lot of these cells in there that will constantly produce more and more of that lining in order to kind of offset the amount of those cells that are dying from that hydrochloric acid burn. So when the protein enters the stomach, the hydrochloric acid is secreted until the pH reaches about 2, which is optimal for a particular enzyme that's going to help to digest those proteins, and we're going to talk about that in a little bit. As you can see here, we have an image of the stomach, and around the stomach we do have the endothelial lining. Endothelial lining inside of those cells. We do have different kinds of cells like mucosal cells and parietal cells you can see here in our image, and these will produce that hydrochloric acid, those gastric juices, in order to help digest, not only digest down a lot of the biomolecules, but also to activate different zymogens or inactive proteins, inactive enzymes, in order to get them turned on and do their job. Okay, acids react with metals to produce salt and hydrogen gas, also reacts with bases to produce a salt and water, and bicarbonate and carbonate ions in order to produce carbon dioxide gas. Now, a salt, as just to recall, is an ionic compound that does not have a hydrogen ion as its cation or a hydroxide ion as its anion. Now, acids here react with metals such as potassium, sodium, calcium, magnesium, aluminum, zinc, iron, and tin. As you can see, to produce hydrogen gas and the salt of the metal, we can see 2 potassium atoms here in its solid form react with hydrochloric acid, and so therefore it will produce a potassium chloride salt and of course hydrogen gas. One of the things which chemists can use in order to determine whether or not a reaction has happened is obviously to detect whether or not gas has been produced, or to detect the production of that particular salt. Zinc and hydrochloric acid can react together as well. As you can see here, the zinc is in its solid form. Hydrochloric acid is dissolved there in water. That's why it's aqueous there. And then we can get zinc chloride and, of course, hydrogen gas as well. Write the balance equations and label the metal, acid, and salt for the following reactions: magnesium metal with hydrochloric acid aqueous, and aluminum metal with that HNO3 aqueous. Now, as you can see here, the magnesium metal with hydrochloric acid, magnesium hydrochloric acid will of course produce a hydrogen gas right over there, and so therefore in producing hydrogen gas, the magnesium and the chlorine are going to react together to produce that salt, MgCl2, and dissolve there in aqueous solution. And same thing here with the aluminum metal with HNO3. We can see we have the aluminum that is reacting with HNO3, which is an acid, and it will produce that salt, 2 moles of AlNO3, 3 aqueous, and of course hydrogen gas is produced as well. Now, the acid, of course, reacts with carbonates and hydrogen carbonates. It also reacts to produce carbon dioxide gas, a salt, and water. As you can see, we have hydrochloric acid and a carbonate, calcium carbonate, and it produces carbon dioxide and water. So those are 2 things I would recommend writing first in this particular kind of reaction, and then determining what that salt is. Of course, calcium chloride would be that salt. Of course, this is the balance equation. Hydrochloric acid as well, reacting with sodium bicarbonate, will produce again carbon dioxide and water, and produces table salt here, sodium chloride. So when you're trying to write the balance equations for these following reactions, for example, in part A, MgCO3 solid with HBr, you can see here that it's going to produce carbon dioxide and water first, and then the salt that's produced is magnesium bromide, MgBr2, and it's dissolved there in aqueous solution. And same thing here with hydrochloric acid and NaHCO3. You can see that carbon dioxide and water are still formed in this reaction, and then the salt here, of course, would be sodium chloride or table salt. In a neutralization reaction, an acid reacts with a base to produce salt and water. So those are two things there, salt and water are produced. Now the salt formed is the anion from the acid and the cation from the base. So anion from the acid here is the chlorine. The cation here is the sodium. So we have here water, H2O, and then of course sodium chloride. In neutralization reactions, one hydrogen ion always reacts with one hydroxide ion. So if we write the strong acid and strong base as ions, we see that hydrogen ion reacts with that hydroxide ion to form that water, leaving the ions sodium and chlorine into solution. You can see here, if we were to split them in their ions, we can combine these together to produce water. And then, of course, we have sodium and chloride. They're split in their ions in aqueous solution. So therefore, the overall reaction occurs as the hydrogen ion from the acid and hydroxide ion from the base forms that water. So here we have that net ionic equation. That is a key reaction that's going on in a neutralization reaction. We have those acids and base and therefore producing water, which we know is a neutral molecule. So here's a guide in order to help balance neutralization reactions. I would definitely recommend writing the reactants and the products, balance the hydrogen ions in the acid and the hydroxide ions in the base, then balance the water with the hydrogen ions and the hydroxide ions, and write the salt with the remaining ions. So as you can see here, if we were to write the balance equation for the neutralization, so the key word here is we know is neutralization of solid magnesium hydroxide and nitric acids. You can see magnesium hydroxide solids written here. We have nitric acid, HNO3 aqueous. If we were to go ahead and balance, first step is to write the reactants and products. Always write out the equation. And the second is to balance it. So we have here, we can balance that hydrogen ion in the acid with the hydroxide ion there in the base. As you can see, we can add 2 HNO3 in order to balance out that H2 right over here. And next, balance the water. Now that the water is balanced, see we have the 2 here, we can balance our 2 H2O. In order to balance here, we have that hydroxide ion there, 2 of them. So we have 2 hydrogens and 2 more hydrogens. They had 4. So in order to get 4, we have to add that coefficient 2 in front of that water. And now write the salt with the remaining ions. The remaining ions here is that magnesium and, of course, the NO3 group. Pull these two together, and then we will get MgNO3 and a 2 right over there. Once again, even though the ions have been split, it doesn't mean that only one NO3 is going to react with one magnesium. You're going to have to determine what the charges of these ions are first, and then determine how many of those particular ions are going to be needed to form that water molecule. And another way to think about it, as we saw in the previous slide, that they actually split into the ions right over here, as you can see, and so you can have 2 ions kind of coming together to form that one molecule. Now select the correct group of coefficients for each of the following neutralization reactions. Step 1 here is to write the reactants and the products. You already know that in a neutralization reaction, water and a salt is formed. That salt, go ahead and write salt first and then determine what that salt is a little bit later. Same thing here with that second reaction. And then balance the hydrogen ions in the acid with the hydroxide ions in the base. So as you can see here, we have 3HCl aqueous, AlOH3, and that salt, and then the H2O right over there. And in comparison to before, we can add that number 3 right over there in front of the hydrochloric acid in order to balance out the number of hydrogen ions with the hydroxide ion in the base. So we have 3 hydrogens here. We should have 3 hydrogens over there. Same thing over here. We have what do we have here? We have 2 hydrogen ions right over here, but 2 times 3, because there are 3 moles of that gives you 6 hydrogen. 6 hydrogen ions over there. So therefore the opposing component right over here better have 6 as well. 2 times 3 gives you 6. And then balance the water with the hydrogen ions and the hydroxide ion, as you can see here. Now that we definitely know that we have three hydrogens here plus another 3 over there, we have a total of 6. We better have a number 3 there in order to balance it out. Same thing here with the second problem we have here, a total of 6 plus 6, so that we have 12 hydrogen ions there. And so therefore over on the product side, we better have 12 hydrogen ions to balance it out as well. And then write the salt. And then as you can see here, the salt, we have aluminum and the chlorine atom right over there. The H here is that acid proton, and we have the OH, which is that basic hydroxide ion right over there. So therefore the two remaining ions here are the aluminum and the chlorine. So put those two together and balance out that molecule, and you'll get the correct amount there. And you can take a look at the second equation and discover the same thing. Let's go ahead and talk about acid-base titration. This is a laboratory procedure used to determine the molarity of an acid, and it uses a base such as sodium hydroxide in order to neutralize a measured volume of an acid, because you already know that when sodium hydroxide is added into water, the sodium acts as a shield for that hydroxide negative ion right over there, and so as it dissolves in water, the water will get in between there and to split those two into their ions, allowing the hydroxide ion to react with whatever it is that's inside of that system. It also requires a few drops of an indicator such as phenolphthalein to identify its endpoints. So you do need that this is known as a type of pH indicator in order to determine whether or not it's hit its acid or its base form. Now, as you can see here, in the following titration, a specified volume of acidic solution is titrated to the endpoint with a known concentration of sodium hydroxide in this particular one right over here. Now, the indicator phenolphthalein is added to identify its endpoint, and it turns pink when the solution there is neutralized. There are different kinds of indicators right over there, as I said earlier. In this case, a phenolphthalein is a pH indicator that resembles that of a neutral solution. It turns pink for a neutral solution. At the endpoints here, the moles of the base are equal to the moles of the acid, because in this particular beaker, you have no clue how much is in there. So in order to help us determine that, you kind of do drop by drop, in this case of a base, and you determine a volume of the base that is used to reach that endpoint, and you can calculate the molarity of the acid and use in the neutralization equation for that particular reaction. So a very useful tool. So here is a guide in order to calculate acid-base titration. Step 1 here is to state the given and needed quantities. Write out your variables and define them. Next, write a plan to calculate the molarity and the volume. Write out all the formulas that you need. Third one here, state the equalities and any conversion factors that you need, including concentrations given in the problem. And then fourth, set up the problem to calculate the needed quantity. So what is the molarity of hydrochloric acid solution if 18.5 milliliters of 0.225 molar sodium hydroxide is required to neutralize 0.0100 liters of hydrochloric acid? So therefore the equation right here is hydrochloric acid, aqueous, mixing with sodium hydroxide, aqueous, gives us that neutralization reaction there, sodium chloride and water. Don't forget, I strongly recommend that when you read these equations, that you look for clue words like neutralize in order to determine what kind of products that you're going to get. So here we go. Step number 1 is to state the given needed quantities and concentration. We definitely know that we're given 18.5 milliliters of 0.225 molar of sodium hydroxide. We definitely also know that we have there 0.0100 liters of hydrochloric acid, and we need the molarity of the hydrochloric acid solution. So we have there an equation that's written for us, which will be tremendously helpful a little bit later. Now write the plan in order to calculate the molarity or the volume. So you are going to, first of all, write down what you know. You already have 18.5 milliliters of 0.225 molar of sodium hydroxide. Then you're going to convert that into liters. Now, once you have liters, then you can use the moles of sodium hydroxide. You can calculate the moles of sodium hydroxide. And then from there, you're going to get the moles of sodium hydroxide and do a mole-to-mole conversion factor, 2 moles of hydrochloric acid. And then you're going to divide that by liters in order to determine the molarity of hydrochloric acid solution. So here we go. We have here some equalities. We definitely want to know that 1 liter is equal to 1,000 milliliters. We have here our conversion factor. And we definitely know that 0.225 moles is equal to 1 liter of sodium hydroxide solution. All right, so we definitely do have that. And how do we figure that out? Is because it's right here. This is 0.22. This is going to be a pain here. Mole per liter. Okay, so therefore 1 liter of sodium hydroxide equal to 0.225 moles of sodium hydroxide, because it's given to us in the equation, guys. It's given to us in the problem. All right, and of course, we have here a balanced equation. That's key. A lot of professors and a lot of instructors like to trick their students by giving them an unbalanced equation. It is your job as a student to not fall for that trick and always balance your equations. Never, never, never forget to balance a chemical equation in any sort of chemistry or biochemistry class. Balance that equation. But in this lucky problem, you already have a balanced equation. So the mole-to-mole conversion here is 1 mole of sodium hydroxide is equal to 1 mole of hydrochloric acid right over there. No problem. All right, so we start out here with 18.5 milliliters of sodium hydroxide. Convert that to liters first. So we definitely have here 1 liter over 1,000 milliliters of sodium hydroxide. Cross cancel those common units that are in the numerator and denominator, and you'll get liters of sodium hydroxide. We're not going to do the calculations just yet. We're just going to write out our units. As I told you guys in lecture, if there's one thing that I hope that you learn from my class is, my goodness, learn how to do unit to unit conversion. Sometimes you're not given a formula, but if you look at the units on a reference page, or if you look at the units given the problem, it can clue you in. It might not give you the whole form, but it could clue you in. You can kind of navigate your way to the correct answer. Okay, so we have here, we want to convert that to moles of sodium hydroxide. Always, 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 always work in moles whenever you're given the chance. If you're doing conversions here, you must work in moles. So convert that into moles over here. 0.225 moles of sodium hydroxide equal to 1 liter. Cross cancel those common units at the numerator and the denominator, and now you're with moles of sodium hydroxide. So now we're getting to this factor over here, and a lot of students have been asked, well, how in the world did you determine that? It's because it's right here in the chemical equation. For every 1 mole that we use of sodium hydroxide in this reaction, we're also going to use equivalently 1 mole of hydrochloric acid. That's where that is coming from. So as you can see here, 1 mole to 1 mole, cross cancel those common units, and then do a little bit of mathematics, and then you're going to be given 0.00416 moles of hydrochloric acid per, and you're wondering where this number come from. Right over here, it's given to us right there in that problem. 0.0100 liters of hydrochloric acid. Follow the sig fig, guys. 3 is a magic number because it is a measurable value right over here, measured value there, giving us 0.416 molar of hydrochloric acid. So there you go. Now you know how to do acid-base titrations. You can go ahead and do the study check on your own. I've already reviewed how to do that. The answer solutions are already provided in the next few slides. Okay, antacids. Let's go ahead and talk about this. Are substances that are used to neutralize excessive stomach acids. And they are made of aluminum hydroxide and magnesium hydroxide mixtures, and these hydroxides are not very soluble in water, so the levels of available hydroxide ion are not damaging to the intestinal tract. So some basic compounds in antacid tablets right over there. For example, we have here Amphogel, which is AlOH3 right over there. Milk of magnesia, you've probably heard of this one. We have right over there. Mylanta, another popular one, antacid right over there, contains these 2 bases right over there. Rolaids, which I haven't seen in quite a while. We definitely do have these bases right over there. And Alka-Seltzer are very common, very popular. There has sodium carbonate and potassium carbonate as well. Let's go ahead and talk about that pH scale. We definitely been mentioning about it throughout the lecture, but we're going to go ahead and get into a little bit more detail about that. Imagine yourself, you already know that the pH is a measure of hydrogen ion concentration in solution. So if I were to ask you, I were to challenge you to find a way in which you can pick up every little hydrogen ion in solution and kind of count them one by one. If you ever discover the way to do that, you need to give me a call, and you and I, we're going to win this Nobel Prize together. But until then, it is virtually impossible to go in there and one by one pull out hydrogen ions and then count them there. So we've got to have an alternative scale in which we can measure the hydrogen ion concentration in solution. Of course, that is that pH scale and is used to describe the acidity of solution. Cranberry juice is very acidic at pH of 2.9. I love cranberry juice, by the way. At the hospital, it's oftentimes for a lot of the patients I've encountered at the hospital who have just given birth to their young infant, absolutely love to drink what we call the splitzer. And the splitzer, and a lot of mothers out there have been asking me, how in the world do you make this a solution? Literally, I just tell them, look, it's just one part cranberry juice and one part 7 Up or Sprite or something like that. Put in some ice, and there you have it. So if you know someone who is just giving birth, you might want to, and they're kind of craving something, might want to ask them to consider this splitzer. Okay, so just something interesting there for you guys to know. Now, the pH of a solution is used to indicate the acidity of solution or the hydrogen ion concentration in that solution, and it has values ranging from 0 to 14, where 0 is the most acidic, and then we have all the way up to their 14, which is the most alkaline or basic. I'm going to put the word base up here because I can't fit the word alkaline there. You're going to see the words alkaline used more in the field because the word base is often confused with, say, the base on a like a home base or a base in a baseball game. So a lot of people confuse those. You'll hear more the word alkaline. Now, it is acidic if the values are less than 7, neutral at 7, and basic if it is greater than 7. As you can see, the way to write that here, pH is less than 7.0 pH for acidic, and we can definitely say that the hydrogen ion concentration is definitely greater than 1 times 10 to the negative 7 molar. And as you can see, that number 7 right over here is right there. So we'll talk about that in a little bit. In neutral solution, the pH is equal to 7. We still have that 7 right over there. It is equal, the hydrogen ion concentration or the hydronium ion is there equal to 1 times 10 to the negative 7 molar. And then we have here a basic solution, which is greater than 7 or less than. 1 times 10 to the negative 7 molar. Excuse me. One of the biggest misconceptions that students have when looking at a pH scale is that they think that the higher the pH, when it goes toward 14, that the more acidic it is. That is absolutely incorrect. And I want everyone right now to take a moment to listen to me right now and remove that from your brain. As the hydrogen ion concentration goes up, the acidity goes up, the pH goes down. Acid go up, pH go down. Acid goes up, pH goes down. Do we get that now? All right, let's move on to the next one. How about base? It's the opposite. Check this out for a base. As the hydrogen ion concentration goes down, it becomes the hydrogen it becomes more basic or less acidic, and therefore the pH goes up. Okay, hydrogen ion goes down, alkalinity goes up. Hydrogen ion concentration goes down, pH goes up. Hydrogen ion concentration goes down, pH goes up. So make sure that you get those connected. So don't confuse those. Students often confuse it. Now, in order to measure the pH of a particular solution, a pH meter is often used in the laboratory in order to give a near exact reading of that particular pH. If you're to take a cell or molecular biology class, you'll have an opportunity to use that. Also, the pH paper is used in order to indicate certain pH values. Is not as accurate as a pH meter because we're using qualitative measures such as color. If a paper turns pink, it's around pH, I don't know, 1 or 2 or whatever, depending on whatever indicator we're using. So you might want, for example, if any of you guys have aquariums, they have these little pH bottles which you can kind of, has little pads, and if you dip into aquarium water, they give different colors. It doesn't give an exact pH, but it gives you a pH range to help you determine what kinds of things you need to do to your aquarium to help give the best living conditions for your fish. Definitely love to raise fish. I have a couple aquariums that I use in order to, and I definitely love raising fish. The pH of a solution is found by comparing the colors of the indicator against that of a chart that's given to you by the manufacturer of that particular thing. Now, the pH of a solution can be determined using, of course, a pH meter, as I've mentioned there a few moments ago. Here's an example of a pH meter. There is a rod right over there and a particular solution. It is measuring that particular pH there. We can definitely use strips, which will change color based upon the pH, and then we can definitely use test tubes. And I actually have one of these kits at home. In my home, in order to measure the pH and the nitrate levels, phosphate levels of my aquarium, but those are kind of fading away because they're quite messy, and they use tablets, and you got to mix them up and do all that kind of stuff. Paper, indicators, pH paper seems to be much faster than that. So here's some pH values of some common household substances right there. Now, if I'm on the pH scale, values below 7.0 are acidic. Once again, at 7.0 is neutral, and above 7.0 are considered alkaline or basic. Alkaline. Okay, that here is basic. For example, hydrochloric acid right over there is around pH of 0. We definitely have gastric juices at 1.6, and lemon juice there 2.2. Lemon juice is at 2.2, guys. My favorite right over here is carbonated beverages like Coca-Cola and Sprite and Dr. Pepper, especially Coca-Cola. Cherry Coca-Cola, definitely my favorite right there. Tons of carbs in that. Anyway, again, around a pH there of a 3.0. Oranges at 3.5. Apple juice, amazingly, right over there is around 3.8. Lots of carbs in apple juice, guys. We definitely here have water, which is around 7.0. Depending on municipal water, like city water, the pH can kind of go up or down a little bit depending on who the water treatment plant is. Blood is at 7.0, which is extremely key. If you were taking my microbiology class, I would definitely want all of my students to know the pH of blood. We definitely have detergents here, which is around 8.0 to 9.0, depending on the manufacturer. Seawater here is at 8.5, which is a basic, water. We have here ammonia, which is at pH of 11, and bleach there is at pH of 12. Extremely alkaline, extremely basic, and of course we have here 1 molar of sodium hydroxide at around pH of 14. Now, does that mean that our scale is restricted to 14 and 0? It can go a little bit above or below, just depending. Okay, but this is kind of the common pH scale. So you can go ahead and identify each of these solutions as either acidic or basic by looking there at each of these. You can see A here we have hydrochloric acid, pH 1.5, pancreatic fluid there at 1 times 10 to the 8. Sprite soft drink, oh my favorite. There a pH equal to 3, pH of 7, and hydroxide ion is equal to 3 times 10 to the negative 10, and we also have here the hydronium ion there at 5 times 10 to the negative 12. And of course the answers are provided right over there for you. Now, in order to calculate the pH of particular solutions, we use an equation known as a logarithmic equation, or it is a logarithmic scale that corresponds to the hydronium ion concentration in aqueous solution, and it is a negative logarithm of a base 10 of a hydronium ion. So pH here is equal. Here's the equation. You might definitely want to know this one. pH here is equal to the negative log of the hydrogen ion concentration in solution. So in order to calculate the pH, the negative powers of 10 in the molar concentration are converted to positive numbers. So if the hydrogen ion is 1 times 10 to the negative 2, you have your pH is equal to negative log of the 1.0 times 10 to the negative 2 molar. And then if you were to do that, plug into your calculator, you're going to get 2. Now, what's also amazing is that you can definitely, if it is 1.0 times 10 to the negative something, you can just look at that number 2, pull it out, and it'll give you the pH as well. To determine the number of significant figures in the pH value, you have to consider the following. The number of decimal places in the pH value is the same as the number of significant figures in its coefficient. So you can see right over there, because the hydrogen ion was measured, so we have to follow the sig figs. The number to the left of the decimal point in the pH value is a power of 10. So you can see we have 2 sig figs, so we better have 2 sig figs there whenever we're writing out our pH. Because a pH is a log scale, a change in 1 unit, for example, from 2 to 3, pH of 2 to 3, okay, will correspond to a tenfold increase, okay, tenfold increase or decrease, a tenfold decrease in hydrogen ion concentration. As you can see here, we have 1.0 times 10 to the negative 2. If I were to write that out in decimal form, it was 0.01. If I were to see here a pH of 3, even though it's going up by one unit value, but if we were to convert that into its molar units here, molar values, we would have 0.001. Okay, and that is 1/10 the value of that of pH of 2. And the same thing here, we go from pH of 3 to 4, even though we're going up by 1, but it is decreasing by 1/10 its value, 0.0001. Okay, 1/10 of its value. So keep that in mind. Don't forget that. So the pH of a solution is calculated from the hydronium ion by using the log key in your calculator and changing the sign. Aspirin, which is salicylic acid, was the first non-steroidal anti-inflammatory drug used to alleviate pain and fever. If a solution of aspirin contains this hydrogen ion concentration, what is its pH? So as you can see here, first of all, you definitely know that the hydrogen ion concentration is 1.7 times 10 to the negative 3. So unfortunately, in this case, you just can't take that number 3 out and slap it, pH is equal to 3, because again, I told you it has to be 1.00, that's it. But we have a different value, so we can't do that anymore. But we do have an equation, pH is equal to the negative log of the hydrogen ion concentration in solution. Go ahead and plug that into, wow, you guys are lucky to plug it into your calculator. pH here is equal to negative log of 1.7 times 10 to the negative 3. So once you plug that into a calculator that works for you, you're definitely going to get something else here, 1.7 times 10 to the negative 0.03. If you were to see that calculated out, you're going to get 2.769551079 in your calculator. Following the sig figs there, it will be to 2 sig figs because we've measured them to 2 sig figs, so therefore it would be 2.77. You can definitely calculate this on your own at home. I've already showed you how to do that problem, but again, the solutions are there. Given the pH of a solution, we can reverse the calculation to obtain the hydrogen ion concentration in solution. So we can definitely go backwards. So as you can see here, the reverse equation here is a hydrogen ion concentration equal to 10 to the negative pH. Right over there, that's our equation. So we have here the pH. Gosh, this drives me nuts. pH there is equal to the negative log of the hydrogen ion concentration. Okay. What is missing here is you don't know that there is a 10 straight on down there. That is the default value that your calculator is going to use. So if we were to divide both sides by negative, we would have a negative pH is equal to log base 10 of hydrogen ion concentration. And then we definitely know that logs are 2 powers. So 10 to the negative pH is equal to the hydrogen ion concentration, which is given right over there. So for pH values that are not whole numbers, a calculation requires a use of the 10 to the x key, which is usually a second function key on most scientific calculators. Here are the 3 steps to calculating the hydrogen ion concentration from the pH. You can see if we were to determine the hydrogen ion concentration from solution for having each of the following, we're going to go ahead and kind of take a look at part B here. 3.42. We have here step one, we need to state the given quantities. We definitely know that the pH here is 3.42. We need the hydrogen ion concentration. We have a formula, so write down that formula. Write down what you know. Write down what you need, and then write down any equations that you need. So for example here, we definitely know that the hydrogen ion concentration is 10 to the negative pH. So we need to first of all write down or type in negative 3.42, and then we use the 10 to the x key on the calculator in order to determine that. The calculator is going to display this massive ridiculous number right over there. But if we were to go ahead and write it out on our paper, we have to do 3.8 times 10 to the negative 4, because we have that negative 4 in our calculator right over there. So that's 10 to the negative 4, 3.8 to 2 sig figs, okay? Because the pH value 3.42 is to 2 significant figures at the decimal right over there, okay? All right, so as you can see, we can definitely compare the hydrogen ion versus the hydroxide ion. Now, what you don't know is that we can definitely calculate the hydroxide ion concentration. We can get the pOH. So here we go. The pOH of solution is equal. Gosh, this pen is driving me nuts. Is equal to the negative log of the concentration of the hydroxide ion in your solution right over there. You can definitely use that equation if a professor might flip-flop them, or me might flip-flop them on you, and I'm asking you, hey, what is the concentration there? All right, so that concludes chapter 10 of the biochemistry of health sciences textbook by Timberlake. Hopefully that you guys find this I almost said medical terminology because I'm so used to doing this for medical terminology. I hope that you guys found this informative. I hope that you catch up with the lecture, because we're going to start right away with whatever we're supposed to. Go ahead and catch up with this, do some practice problems in the book, and I will see you guys next time.